Maggie Hurwitz from National Weather Service headquarters, and this webinar is an extension to the 2023-2024 joint webinar series that we, the Weather Service, have done with NIDIS, the National Integrated Drought Information System. So we're happy to provide that today, June 30th, 2025, or whenever you're listening to this recording. Next slide, please.
Great.
So today, thank you. Thank you. I'll hand it off to Mary Wallison from NIDIS to share the agenda for today's webinar.
Hi, everyone. Thank you for joining us today. I'm Molly Wolozin, as Maggie said, and I'm with the Cooperative Institute for Research in Environmental Sciences, or CIRES, and also NOAA's National Integrated Drought Information System. So on today's webinar, we are going to start with a presentation from our partners at NASA. They'll be presenting the research and the key takeaways from around quantifying the importance of selected drought indicators with respect to the U.S. Drought Monitor. So we have Sony Yathendradas from NASA Goddard Space Flight Center and the University of Maryland, and also David Mako with NASA and SAIC. After their presentation, myself and Kelsey Eichste, also with CIRES and NIDIS, will give a brief overview of how to access the key drought indicators for your work moving forward. And then we will also have a moderated Q&A at the end. So I will go ahead and turn it over to Sony and David for the presentation, and also want to acknowledge Amy McNally and also Krista Peters-Ladard from NASA as well for their collaboration on this project. So Sony, I will turn it over to you.
Yes, hi everyone. This is Sony Yathendradas and David Moko from the NASA team. We'll be talking about the research overview and key findings by region. Dr. Krista Peters-Ladard was the PI for the first phase of the project, which was dealing with the coarser spatial scales, and then currently it's Dr. Amy McNally, who's the PI for the finer spatial resolutions phase of this project. Next slide, please. So a quick introduction. We all know that drought monitoring is complex and involves tracking multiple indicators like precipitation, evapotranspiration, soil moisture, etc. And for any given indicator, it may vary depending on the location, the climate, and the geography, the time of the year, the historical drought impacts, and multiple other factors. So a drought in Arizona, for example, is very different from the drought in Alaska. Now, for supporting more effective drought planning, decision making, and communications, we would like to know how relevant is each drought indicator to the drought for specific regions and seasons. Now, multi-indicator products like the US Drought Monitor and Drought Blends, etc., they give a more complete picture of the drought conditions because of using multiple indicators. However, we don't know the importance or relevance of individual indicators to these assessments, which is where our research came in. Next slide, please. So a quick overview about the research that we did. We quantified the relative importance as a proxy of the drought representativeness of specific indicator or set of indicators with respect to the US Drought Monitor. And for this, we took 113 different indicators of drought, including in situ, modeled, and remotely sensed data, and used an information theoretic measure called the mutual information to compare these indicators to the USDM for a period from 2006 to 2019. And we broke those down into by geographic region and by season in the first phase, and published the results in the Journal of Hydrometeorology. The DOI for that is given in the rectangular text box at the bottom of the slide. The picture on the right is a US Drought Monitor. Next slide, please. This is a quick sidebar. We use mutual information because this is a data only metric, and so it is a more fundamental measure as compared to finding the indicator importances based on machine learning techniques, because there the individual machine learning model structures also come into play, and so can be different for different machine learning techniques. So coming back to the mutual information, it is based on entropy, which is a measure of the information contained in any given variable. In our case, we want the common information between two variables. One is the USDM, and the other one is the individual indicator or set of indicators that we are interested in. And so you can see in the figure to the right, the left green circle denotes the entropy of the given indicator or indicators of interest, and on the right circle is the yellow circle is the entropy of the USDM, and the common region, the light green, is the mutual information that we are interested in. And what we do also, and shown in the formula at the bottom, is to take this mutual information and divide it by the entropy of the USDM to normalize it so that we are able to compare it across different regions and seasons. Next slide, please. There are some caveats to this research. The first one is that going back, this research uses the US drought monitor as the truth or the training target, and the time period is 2006 to 2019. And so the acknowledgements or caveats related to this is, first, yes, the USDM is the definitive source of drought information for the entire United States. But it's important to keep in mind that it's created by a rotating set of authors using both objective information and subjective information based on expertise and local input. Not all the indicators used by the USDM authors were included in this study, and the indicators that the USDM authors use have changed over time. For example, as new data sets become available, or as the spatial resolutions of any indicator goes into finer ones. And yeah, so because we are using the USDM for this time period, so of course, if we use a different target or a different time range, it can produce different FI values, fractional information values, just like with any other technique. At the bottom of the slide, the bold text, we just want to emphasize that this study cannot tell us which data sets the USDM authors necessarily used, but it can tell us which data sets are correlated with the USDM. Next slide, please. This slide lists all the 113 indicators that we used. The left panel is the 39 observation based, middle panel is the 53 model based, and the right panel is the 21 remotely sensed based. And any indicator, for example, precipitation, if we take the left sub panel, the NCI and claim grade monthly precipitation, it has different time scales, and each time scale has been counted as a separate indicator in the study. And you can see here on this slide that we have a wide range of indicators that we have used. Next slide, please. Going on to the methodology. So as we mentioned, we calculate the MI or the FI for each of the indicators or sets of indicators. For example, we can take all the remotely sensed indicators and find the fractional information of that. We started out at coarser spatial scales, where we use the climate division resolution percentiles, took their collections to calculate the fractional information for the NOAA regional climate center regions pictured on the bottom part of the slide. And in the second phase, we also calculated the FI at higher spatial resolutions, that is for the climate divisions themselves, and at the enclave grid resolution of 4.6 kilometers. And just to quickly, sorry, yeah, just to quickly note, between the western region and the high plains region, there is a common region comprising both Colorado, sub-region comprising both Colorado and Wyoming. That's included in both the regions. Next slide. Thank you. Coming to overall takeaways. So first thing we noticed was that no individual indicator can define drought on its own, and this is more pertinent at the regional scale. So at the regional scale, even the highest FI values that we are getting, they explain only 40% of the information in the USDM. But when we start to combine multiple indicators into multi-indicator sets, then we start to get information that is closer closer to the full information of the USDM, something like 60 to 80%. Um, and then from there, when in each multi-indicator set, we had a question about, can we take the top indicators and can we still capture most of that drought information? So that is what is mentioned in the bottom left box, text box, where we did a quick and dirty simply taking the top 15 drought indicators and then quantifying the information. How much do they capture? So they do lose some information, but they still have a lot of the information captured, which is very encouraging. So this means that if someone wants to take the top indicators in a different way, for example, indicators which do not have common information among themselves and then combine them, this could actually increase, capture further information of the USDM. And then bottom right text. So here we took the remotely sensed and the model indicators set separately, and then we were seeing that we were able to capture most of the information of the USDM, which was helpful. So this means that we can construct remotely sensed only or modeled only drought products, and this can still be very effective, and this is very valuable in station scarce regions. And I think so. And I'm turning it over to David for the next slide.
Yeah, hello, this is David Mako at NASA Goddard and with SAIC as well. So we wanted to summarize some key takeaways for some of these different regions. And first, we're just going to show the Midwest. And what's depicted here are the top 15 indicators. Now, we're not showing the particular FI scores here. Those details are in the paper if you wanted to go in here. But here are just very simply are the top 15 indicators. And as you can see, 9 of them are soil moisture based. A lot of the NLDAS, soil moisture, whether it's 1 meter or total column, soil moisture had the highest fractional information in this region for the entire year compared to the US Drought Monitor. And then for precipitation, you see precipitation at the 2 to 3 month time scales, whether it's the actual precipitation or the SPI. So you see the shorter 2 to 3 month time scales. And you also see the SPEI, which also includes the evapotranspiration. That's also with the 3 month scale, as well as the Palmer Modified Drought Index. So when you take them together, you can see how nine out of the 15 are soil moisture, and 4 out of the 15 are precipitation, which is probably not too surprising, but this is quantified and detailed further in the paper. Next slide, please. So again, the precipitation, the SPI and SPEI, they do appear within the top 15 for every season when we break it down by season: fall, winter, spring, summer. The timescales do vary. So in the winter, it turns out actually longer timescales are more relevant to the drought when we look just at winter months, and then spring up to 9 months, and then more shorter scales in the summer and in the fall, which shows the importance of that short-term precipitation and SPEI in that summer warm period. Of course, soil moisture is important. Runoff appears in every season except for in summer. And then groundwater is also important in the winter, and the Palmer indicators are important in the winter and spring as well. Next slide, please. So here's just an example for breaking it down for the Midwest region. We're not going to show this for every region because we don't have the time, but the slides that we'll share will have this for every region as well. So again, this is the same as before, only on the left side, we're only looking at the summer months. And you can see, again, soil moisture is quite important. You see the shorter time scales of the precipitation and the SPEI. The falls, again, very similar with the shorter time scales and soil moisture being important. but now you see runoff as one of the top 15 indicators, and the PMDI as well. Next slide, please. Then when you go into winter and spring, you see the palmers are quite relevant. You know, they have the highest FIs to the USDM during the winter in the Midwest. Then you see some longer precipitation timescales. You see runoff and groundwater. Soil moisture again is still 5 out of 15 in the top 15. And then by spring, you have more like a 9-month, 6 to 9 month time scale for precip and SPEI. Soil moisture, of course, is very important still with the palmers and runoff as well. Next slide, please. So just some key takeaways for the West. Now you see longer time scales for precipitation and SPI. You see 9 to even up to 24-month time scales have the highest FI when it comes to the USDM. Groundwater is one of the top indicators. The palmers, again, are very important. And then you also see a couple soil moistures, but here mostly column, not top 1 meter. SPEI is actually one of the top indicators for all seasons, so showing how important the SPEI is out west. Next slide. For the high plains, some of the key takeaways, again, soil moisture was pretty consistent across all seasons. The palmers as well, and you see more like a 9 to 12 month time scale for the precipitation and the SPEI for the high plains region. Next slide, please. For the south, this again, 9 out of 15 were soil moisture, both 1 meter, top 1 meter, and total column. The palmer indicators, but the runoff is actually very key in this region as well. You can see how multiple different runoff products have made it into the top 15 to have the highest FI compared to the USDM. Typically, the shorter timescales for the precip are also important in the south. Next slide. For the Northeast, again, very short timescales were generally the most important, and the runoff also was in the top 15 again. We typically see like a 2 to 3, maybe even up to 6 month timescales for the SPEI and the SPI and precip. Again, the palmers are in there as well, but runoff, especially seasonally, is quite important in the Northeast. Next slide, please. For the Southeast, we see typically 3 to month timescales for the precip and the SPI. We see runoff, and we also see the palmer indices as well as, of course, the soil moisture. Next slide, please. All right, for the next few, I'm going to pass it back to Sony.
Yeah, so thanks, David. The slides that David presented, these were from the regional scale from that publication. And this slide is just an example of how the results might change a little bit when you go from the coastal regions, the coastal scale regions, which is the top left subplot. This is for that regional scale of the NOAA Regional Climate Center regions, going towards finer scales. So for finer resolution. So the right plot is top right subplot is for climate divisions, and the bottom one is for the unclaimed grid. All 3 plots are for an example indicator of the 12-month NCI precipitation, and this is data for all the seasons together. We can see here the contrast going from the coarser to the final resolutions, where we can see more detail, but also in the top left in the top left subplot with the regions, when we see the US West region across the entire region, and this is probably the largest region in this set, the FI value is pretty low. And when we contrast, and this is even for the California location, but when we see the same location for the top right and the bottom subplots, we can see that the FI values have significantly increased from those values. So yes, just wanted to show this contrast slide across resolutions. And next slide, please. This is again what you have mentioned before, touched on a bit in the earlier slides. So the previous slide was individual drought indicators, and this slide is for multiple drought indicators. So sets of indicators together, and for the regional scale. This row of subplots, the y-axis is the fractional information, the FI values, and the x-axis is for each region, as well as events. We also analyzed events in the paper, but we have not presented that here. Now, each subplot is for each set of indicators. So the top left is for all 113, the middle one is for remotely sensed, and the top right is for modeled and mainly for the model-based indicators. So taking all the 113 together in the top left subplot, we can see that this is 60 to 80%, 60 to 80%, and even more of the information of the USDM that is captured. Now, when we take smaller subsets of this, in the middle subplot, it's remotely sensed only, and the right one is modeled only. We can see that the fractional information decreases a bit, but it is still pretty high. Just wanted to mention that along with the orange bars, the individual dots are for each season on each bar. And then going to the next row of subplots at the bottom. Yeah, so here what we did was for each bar or dot from the top subplot, we took only the top 15 indicators, the quick and dirty method that we mentioned. And we can see here that, yes, the FI goes down, but there's still a good portion of the information that is captured. And as I mentioned before in the earlier slides, if we can do a judicious selection of the top 15 indicators instead of this quick and dirty method, it can actually go up. And this is great for drought monitoring and prediction in regions with in situ, with limited in situ data. Next slide, please. And just to wrap it up, the main findings of this research. So number one, we were able to rank the drought indicators by region and season. Number two, at the regional scale, when we take together sets of indicators or even the top 15, we are able to capture 50 to 80% of the combined information of the USDM. Number three, if we take individual indicators and the associated processes that are associated processes with those indicators, then we were able to get some insights about the dominating hydrological mechanisms for droughts in the paper. Number four, if you use only model-based indicators, it performed well, which shows a promise for effective drought prediction and possibly even forecasting. And finally, using only remotely sensed indicators shows value for drought monitoring, even at in situ data scarce locations. With that, I turn it over to Kelsey and Molly.
Great. Thank you. Yes, thank you so much, Sony and David, for your presentation. So to wrap up the webinar, Kelsey and I will be walking through how to access some of these key drought indicators. So just as you well, actually, sorry, before I jump into that, I wanted to briefly talk about where NIDIS is going next with this research. So if you remember a few slides ago, Sony had shown the difference between the different scales, the regional information that was presented, and then we have climate division and also NCLIME grid resolution scale data for this research. So NIDIS is now receiving all of that data at the different scales, and our goal is to help distribute the findings of this research in order to help decision making, drought planning, and communications. So we are in the process of developing interactive tools and data visualizations for drought.gov that can help showcase some of this research at various scales. We're also talking about other ways of providing this information, whether that's through a story map or other interactive web communication to help us explain the results of this research for different audiences, including the public. And also we are going to make the data publicly available to download as well. So if anyone's interested in continuing the research or incorporating some of this into their own work, we will have that available. The figures on the right are just showing some mock-ups of potentially what this could look like on drought.gov. So for instance, we might have it, you can filter by region and also select if you want to view the top indicators or different types of indicators, and it will give you a general sense of what the FI values are for that region. And again, we have this available at the Climate Division and also the 4-kilometer grid resolution, which we're hoping to make available on drought.gov. So more to come in the future on that. But for right now, we did want to walk you through where to get some of the top indicators. And so you likely noticed as David was presenting that while each region is a little bit different in terms of the importance of the different indicators, there are some indicators that came out across all of the different regions. So we're going to just quickly walk through a reminder of what those indicators are and also some different ways to access data to incorporate into the work that you do, whether that's through your drought information statements with your weather forecast office, or if you do provide input into your state process for the U.S. Drought Monitor. These are just some additional data sets and access that you can use. So first, I'll start with soil moisture. So soil moisture data is available in different ways, most commonly whether that's through observations or in situ data, satellite technologies, and also models. And there are products that utilize more than one, so they may integrate and incorporate observations, satellite, and or models into one product. The common depths that you can get soil moisture data include the surface layer, the top 1 meter or root zone, or the entire column. So Kelsey put some links into the chat box. The QR code on the screen is to the soil moisture product dashboard from drought.gov. And on that dashboard, you can get access to various products for soil moisture, including those that were included in this study, the CPC, NLDAS, NOAA data set, but also other products, including NASA Sportless, Crop CASMA, and the GRACE soil moisture data as well. So I did want to mention just one caveat, especially if you're looking at this product dashboard of all the different soil moisture products. It's important to remember that you're not necessarily comparing apples to apples between these products. So there might be differences in terms of if they're looking at percentiles or anomalies. There might be differences in depths. So just a caveat that you definitely want to look at the product descriptions that are available in order to know exactly what you are looking at. And because the maps potentially show different things, we also wanted to mention that a best practice that I use and I know others use is that I look at a variety of sources for soil moisture data and see kind of where the consistency exists. So if a few products are showing dry in one area, then I'm likely to believe that or have more confidence in that. So the other links that Kelsey put into the chat box, the CPC soil moisture, and then also the NASA NLDAS soil moisture maps as well. So Kelsey, I'll turn it over to you for the next couple of slides.
Thanks, Molly. So the next couple of slides cover a few different drought indices or calculations that combine multiple drought indicators together, like precipitation, temperature, etc. So the standardized precipitation index came up a lot in the study, or SPI, and this is a drought index that captures how observed precipitation deviates from the climatological average over a given time period. You can view SPI at a variety of different timescales or based on different underlying precipitation data sets. The image that's on the screen here is of a 3-month standardized precipitation index. And in this case, the standardized precipitation index is binned into different percentile categories to show dry or wet conditions. The 3 QR codes on the screen are 3 different sources out of many where you can access SPI maps that are readily available to use in communications. The first is Standardized Precipitation Index from the National Centers for Environmental Information's NClimaGrid dataset. So this is available on drought.gov, and that QR code and the link in the chat will also take you to a data catalog page with some additional information and documentation on like what is SPI and how is it calculated, as well as data access. But then I also included a couple other links to some of NOAA's regional climate center websites, and a number of the regional climate centers have SPI maps readily available to use. The Southern Regional Climate Center has SPI maps going up to, I believe, 36 months on the Integrated Water Portal, and the High Plains Regional Climate Center's ACES climate maps have SPI going up to 60 months, and this is not just for the Southern and the High Plains region. Both of these RCCs have these maps for specific regions of the country across the United States. Next slide, please. Another drought index that came up a lot in this study is the Standardized Precipitation Evapotranspiration Index, or SPEI. Now, SPEI is calculated in a very similar way to SPI. The main difference is that while SPI just takes into account precipitation, SPEI takes into account both precipitation and potential evapotranspiration. So it's looking at both the supply of the water as well as the atmospheric demand. And this is important because warmer temperatures can increase evapotranspiration, which can dry the landscape and contribute to drought conditions. Actually, scientists have identified evapotranspiration and soil moisture as early warning indicators for the development of flash drought, or rapid onset or rapidly intensifying drought. Unlike slower evolving droughts, which can be caused by a decline in precipitation and other water supplies, flash drought occurs when
listening to a webinar. It's okay.
Oh, I think there's a little bit of getting a little feedback if folks could mute themselves. Flash drought can occur when low precipitation is accompanied by high temperatures, high winds, changes in radiation, and this can raise evapotranspiration rates and remove available water from the landscape quickly. Evapotranspiration can also play a big role in other droughts as well, not just flash drought. So that's when SPEI could be a particularly useful tool. This, just like SPI, is available in a variety of different timescales. We've included links to view SPEI from drought.gov based on NCEI and ClimaGrid precipitation data, as well as from different regional climate centers. Next slide. One of the other big indicators that showed up throughout this study was precipitation. Now, obviously, as National Weather Service staff, I don't need to tell you all where to find precipitation data, but I did want to highlight just one special feature that NIDIS and the Drought.gov team have actually developed for the National Weather Service weather forecast offices. We've created custom maps for both NWIPS and MRMS precipitation data from the Weather Service that are zoomed in on specific regions and overlaid with WFO boundaries. The QR code on this slide, as well as the link that we'll put in the chat, link to a Google Sheet that has the URLs for all of these custom map images, which are publicly accessible. The Google Sheet, you need to have a NOAA.gov email to access, but even if you're not affiliated with the WFO, we would be happy for you to use these custom images that we've created. Each of them has a static URL, which updates daily around noon Eastern time or so. So you'll have the latest available data. And again, so these are just taking publicly existing precipitation data sets and customizing them for the National Weather Service regions. We have a variety of other maps on there as well, like the U.S. Drought Monitor, Quantitative Precipitation Forecast, and Climate Prediction Center outlooks. Next slide.
Okay, I will take it back over from here. So the next indicator is groundwater data. And groundwater data can typically be found in two different formats, whether that's through observations available through the U.S. Geological Survey or through products that utilize both satellite and or modeled data. The example that we included in this study is the GRACE groundwater drought indicator. So quickly going back to the groundwater observations available from the U.S. Geological Survey, the QR code on the screen is providing access to a data portal that shows the percentiles of groundwater observations. Groundwater can be a little bit of a trickier indicator to interpret, especially if you are looking at direct observations. And so if you go to the main USGS website, their information and data might look a little bit different than you see here on this screen. This data portal in particular is to give us a snapshot at what the percentiles are. So a lot of times the data you're looking at on the USGS website might be referencing the depth to the water level. And so just be aware of what you're looking at. But we included this one because we find it to be the most useful when it comes to drought monitoring. On this data portal, you can also filter by stations that are in their climate reference network. And so those are stations a little bit lower density, but they are stations that likely are not impacted by water use and irrigation. So they would be able to give you more of an idea of if that groundwater is being affected by drought or other conditions. So again, we also have another product because the observations can be a little scarce with groundwater. There are other products available like the GRACE Groundwater Drought Indicator available from NASA and the University of Nebraska-Lincoln. And again, that's the groundwater data that was included in this study. And so these maps, one is shown here on the screen as an example, provides the drought indicator reference for groundwater where you can see if it's dry or wet at that given time. So finally, we wanted to point you to the various Palmer indices that are available. So in the study, we included the Palmer Modified Drought Index, or PMDI, and also the Palmer Hydrological Drought Index, or PHDI. And those are shown on the right. But both of those are based on the original Palmer Index, which is the Palmer Drought Severity Index, or PDSI. So you can access PDSI through various ways. We provided the QR code here to access it through drought.gov, where you have higher resolution, lower latency graphs or graphics, of PDSI. So the strength of PDSI is that it is good at assessing longer term drought, and it does take into account the prior month's conditions. So when you compare PDSI to the other two indicators, PMDI and PHDI, I would say it is more readily available. That's why we wanted to include it as a resource. And again, it typically does have lower latency and higher resolution as well. So that's a little bit better for real-time monitoring. But I did want to show where you can get the PMDI and PHDI because they showed up as pretty key indicators across most of the regions. So the Palmer Modified Drought Index is based on the original PDSI, and it's modified to be less sensitive during transitions between wet and dry periods. So oftentimes the two indicators of PDSI and PMDI are similar during drought and wet periods, but they differ when shifting between them. Also, the Palmer Hydrological Drought Index was, again, based on the original, but modified to take into account longer-term dryness, and it's designed specifically to capture hydrological impacts, like water storage, stream flow, and groundwater. So both of these indicators can be accessed through the NCEI website that actually includes all the Palmer indices, and the maps are available at the monthly time scale. Okay, so to wrap us up here, we really appreciate you joining us today to hear the key takeaways from the research at the regional scale, and then hopefully you saw some value in in us providing information on how to access the drought indicators as well. As we mentioned while David and Sony were presenting, we only gave an example of one of the seasonal results that we have because of time, but we do have seasonal results for all of the seasons. And so we do plan on sharing the full slide deck with that seasonal information with all of the registrants for today's webinar, and we will share that with you by email within the next couple of weeks. And also the QR code on the screen is if you are interested in providing more information for this study as we start to transfer the results to drought.gov, or just want to stay in the loop more on this project, please go ahead and put your information in, and we will make sure to contact you in the future. And if you do have any questions, myself or Kelsey are happy to help you, and our emails are on the screen. And I think, Kelsey, did you want to mention something?
Yeah, we have a question in the chat. I think we have maybe if have time for a couple of questions before we wrap.
Yes, we do. Okay, so the questions here.
I'm
Go
happy
ahead.
to read
Yeah,
it.
why don't you? Yeah, go ahead.
So we got a question. How far ahead are the drought predictions? Are there indicators of uncertainty? And then a follow-up. The mutual indicators technique discussed in the first part of the presentation, are these predictions or just indicating the current state of drought?
Yeah, so I think I don't know, David or Sony, if one of you would like to take that, but it for the study we did look at the time period of 2006 to 2019. So I believe we are just looking at in this study not the current state, but historical drought to assess the relationships. But David or Sony, would you like to take that
Yeah,
on?
this is David. That's a good question, and it's something due to time we didn't go into a lot of detail about. So when we calculated the mutual information, we actually compared the USDM weekly data to each individual indicator's weekly data for that period, 2006 and 2019. That's how we calculated the mutual information and then normalized it to get the fractional information. So it's not a prediction. It's just in terms of you have the drought monitor every week during that period. You have the indicator during that period for every week. How much information in that indicator, how much does it explain of the USDM? And that's where we got those FI values. So it's a more of a monitoring thing right now. It's just, you have the indicators for that period, and then how much information is common with the USDM for that same period. I hope that addresses the question. And there was another question as well that sort of related, I guess. How far ahead are the predictions? So, as I mentioned, they're not really predictions. It's just the common information during that 2006 to 2019 period. As far as uncertainty, we didn't calculate necessarily an uncertainty within the fractional information that was calculated. It's just, we can refer back to the caveats in terms of some of the, known potential areas where the FI might not be fully representative because, we didn't capture the local expertise, doesn't capture the, the local input and the drought monitor author skill necessarily. But, and of course we do have 113 indicators, but we don't have every indicator in our particular study. I hope that addresses the questions. If not, please let me know.
Yeah, I think that was, yeah. Sony, did you have something to add?
Yeah, I just wanted to add that for the two coarser spatial scales or resolutions of the regional scale um, and climate divisions, we reran that to give uncertainty also in DFA values. So those should also be available. We did not do that for the finest one and Climbrid. It was too computationally intensive, and going back and running that will take too long. So, yeah.
Okay, yes, Maggie.
Sure. Well, thank you first to Sony and David. Great presentations, and of course to Molly and Kelsey for sharing how to find these indicators. Just a reminder before my question that we're still welcoming questions in the Q&A box here. So for Sony and David, I wonder, we're in a non-stationary climate, and climate change is happening at different rates across the country. But I wonder if we look ahead, 10 or 20 years, would you expect to see similar relationships of the most important drought indicators in these regions, or do you think they would change, and how so?
Yeah, this is Sony. So we do expect the FIs to change as the climate changes